Alright, so we have a really weird looking function and we want to figure out how to integrate it. So the first thing that I would recommend when looking at a problem like this is to actually sort of try to figure out what this function actually looks like. So here this is 1, this is 1, this is 1/2, this is a third, this is 2/3, etc. So these are the y values and these are the x values. So let's see here, so it's going to be 0 at most points, but it could be 1 over q if x is rational and y is p over q. So let's see here, and that's in lowest terms. So if y is 1, then the function will be 1. So if we look at this line here, so here f equals 1 sometimes. Because along this line here, where y equals 1, f will equal 1, but only when x is rational. That's actually a really interesting point. Why does x need to be rational? I'm not actually convinced that it does need to be rational. Oh, maybe it does. Maybe it doesn't. Let's not worry about it. Okay, so over here, on this line, where y equals 1/2, then f is going to be 1/2 whenever x is rational. Similarly, here f is going to be 1/3, and here f is going to be 1/3. So we sort of have these horizontal lines where f is sometimes equal to a value, and it starts out up here it could be 1, here it could be 1/2, and then as the denominator grows, you get more and more potential lines, but the value of f on those lines gets smaller and smaller. Okay, so my idea here is to basically find a partition of this domain, and basically what we're going to do is we're going to start by putting a rectangle around that horizontal line, and then one around this 1/2, and then we get some rectangles around the 1/3 and the 2/3, and we keep going. And we want to try to make these rectangles really thin. So anyways, given delta greater than 0 and some natural number n, of course natural numbers here don't include 1 because I'm an analyst. Don't include 1. Natural numbers don't include 0 for me. So natural numbers are 1, 2, 3, etc. So let P be the following partition of this box from 0 to 1, 0, 1, cross 0, 1. So if I is between 1 and n, then P contains, so this is going to be Pn. Now, well, P depends on both delta and n, so let's just not write any of those things, but it's implied that P depends on both delta and n. So P contains rectangles which cover 0, 1, cross 1 over n, through 0, 1, cross n minus 1 over n, without overlap. So basically, what I mean by without overlap is that if we look at like n equals 4, so we want to cover 0, 1 cross a fourth, cross 0, 1, or we want to cover 0, 1 cross a fourth. We also want to cover 0, 1 cross 2 fourths. Well, 2 fourths is 1/2, and we would have already covered 0. We would have already covered 0, 1 cross 1/2 when we were at the I equals 2 case. So you sort of start at I equals 1 and continue inductively to I equals n, and you don't cover anything that was already covered by a previous smaller value of I. Okay, without overlap. So rectangles which cover this thing and whose total volume is at most delta times 2 to the minus n. And this is possible because the y-coordinate is just a single point. So we can make this interval as thin as we need to in order to ensure that when we add all these up, the volume is going to be less than, or rather I've written at most, delta times 2 to the minus n. So that's for I equals 1 to n, but this will only cover part of the part of this two-dimensional square. So P covers the remainder of 0, 1 squared arbitrarily. Because we've only thrown in finitely many rectangles for I equals 1 to n, you can just throw finitely many more in to cover the rest of it. Okay, so now we want to actually compute, we want to, given an epsilon, we want to find a partition of this form, which we can get the upper sum minus the lower sum to be as small as we want. Okay, so anyways, given epsilon greater than 0, choose delta and n such that, okay, of course, delta must be greater than 0 and n must be a natural number, but we want delta and 1 over n plus 1 to both be less than epsilon over 2. Then, okay, first of all, if we look at LFP, what will this be? Well, any rectangle will guaranteed contain a point with an irrational x value and an irrational y value. And so the infimum will guaranteed be 0. Wow, look at this cool guy. There is someone outside who is very cool. You can tell by the loudness of their motorcycle. It's just, wow, I'm impressed. I'm so impressed. I cannot focus on math right now. Just kidding. I can, and I will. So we have the lower sum is, because every rectangle is going to contain a point with irrational coordinates, it will be 0 there, and so the infimum is going to be 0. So you add all of these terms up in the lower sum and it'll give you 0. And we also have the upper sum. We can estimate this. Okay, so let's think about this. What is the upper sum going to look like? So this will be less than or equal to. Okay, so we first look at these for I equals 1 to n. We want to sum up what the supremum over these rectangles times their volumes will be. So these are the rectangles. Let me think about this. Did I mess something up here? So the sum from I equals 1 to n. So if you look at any particular I, you're covering 0, 1 cross 1 over I through 0, 1 cross I minus 1 over I. So, and then the supremum is, well, let's see here. So the denominator here is I. And so it's going to be 1 over I is going to be the maximum value, because the minimum value would be 0. The maximum value would be this thing. The only way it could go over would be if you can reduce the fraction at all, in which case it would have been taken care of by a smaller I value. So it's 1 over I, and the volume is delta times 2 to the minus I plus 1 over I times delta 2 to the minus I. And this sum is the thing that I didn't actually consider. So we have to sum these up, because for each I, oh no, the total volume is at most this thing. So we can sort of consider all of these at once. So if you consider all of the rectangles which cover anything of the form 0, 1 cross 1 over, any rectangle which covers something of the form 0, 1 cross k over I for k between 1 and I minus 1, then the total volume is going to be less than delta times 2 to the minus I. And the maximum value over these rectangles will be 1 over I. So we indeed have this sum. Okay, so I was correct. And in fact, this is a less than or equal to, because this is if this sum would hold if we don't throw out any of the rectangles. But indeed, we needed to throw some of them out because we would get some overlap. For example, like I talked about with the 1/4. Once you get to 2/4, you have to throw that one out because you're already covering 1/2. But anyway, so we have this sum, and that's what's covered by I equals 1 to n. Plus, and now we have to consider everything that's covered by the remainder. So what could be the largest possible value on the remainder? Well, anything with the denominator less than or equal to n has already been covered. So the denominator can be at least n plus 1. So the maximum value on the remainder is 1 over n plus 1. And what's the volume of the remaining space that's being covered? We take the volume of the entire space, 1, and then we subtract the maximum volume that could have been covered already, which is sum from I equals 1 to n, delta 2 to the minus I. Now let me think about this though. So we may have covered less than that. Right? We may have covered less area than that. So this actually isn't true. Because if you cover less area before, then this 1 over n plus 1 needs to account for more area. So I think we have to drop this out and just assume that the remainder has size 1. Okay, let's hope this still works. Oh, well then it's actually easier to prove this. Because look, we factor out the 1 over I is going to be less than or equal to 1, and we can pull the delta out front. So we have delta times the sum from I equals 1 to n of 2 to the minus I. And that's going to be 1/2 plus 1/4 plus etc., etc. And that infinite sum is going to be equal to 1. And so if you cut it short, if you cut it short, then it's not going to be equal to 1. It'll be slightly less than 1. So that will be less than or equal to if we just replace it with 1. Then we have this delta plus 1 over n plus 1 but we chose this so that this is less than, delta is less than epsilon over 2, and 1 over n plus 1 is less than epsilon over 2, and this is precisely epsilon. Okay? So, 0 is less than or equal to L Fp, which is always less than or equal to U Fp. No. Yes. Because we're not only proving integrability, but we're going straight to the actual value of the integral. 0 is less than or equal to LFP. No, 0 is equal to LFP, which is less than or equal to U Fp, which is less than epsilon. So if we take 0, so the supremum of LFP is going to be 0 if it's equal to 0 for every single p. And then if we take the infimum over all UFP, then because we can choose, given any epsilon, we can choose a partition such that U of Fp is less than epsilon. The infimum must be smaller than any positive number, and so it must be 0. And so this tells us precisely that not only is F integrable, but the integral is precisely 0. So yeah. So again, I'm looking back at this. This function says that f needs to be 1 over q if x is rational and if y equals p over q in lowest terms. I don't think we need to restrict x to being rational here. I think x could be irrational, and this still holds because you're still only defining f to be 1 over q on a horizontal line segment, which has Lebesgue, which intuitively for me has Lebesgue measure 0, and so it can't really contribute anything to the integral. But even for our purposes, any cover of any of these horizontal line segments will contain points where the y value is irrational, and so you're always going to have 0 in there, and so the lower sum is always going to be 0. And of course, the upper sum isn't going to change at all. So I think that you can have a function, you think you could define f to be differently, i.e., in fact, you can define f to be non-zero on a larger set and still have the same result using this same exact proof. Another interesting thing about this is that we got this partition that we chose. It did a really good job of covering everything. Like, all we had to do was choose an n large enough and a delta small enough, and it works. I'm sort of surprised at how well this works. Usually, sometimes in analysis you don't really have a lot of leeway. I feel like this is sort of a rough estimate, if that makes sense. I don't know. It's sort of like a, I don't know. It's certainly interesting though, and this is a really nice exercise for making you think about functions with strange definitions and how you can approach them with these sort of delta epsilon types of approaches. Well, this isn't really a delta. Sure, it uses the delta and an epsilon, but it's about estimates and how can you estimate things. And how can you get error bounds on things? And so this is, of course, important in things like integration, but it becomes much more important when you move on, if you move on to things like other things in real analysis, like principles of mathematical analysis or Baby Rudin, and also like eventually measure theory with Fallen's textbook or a similar textbook. But yeah. So anyways, here's a strange looking function, and we've computed its integral, and so now we are done.